So we know about the standard map function in Haskell, right? That says if you give it a function from A's to B's, and then a list of A, you can turn it into a list of B by applying that function to every item in the list. And we also wrote versions of this for other types. For example, we had some kind of tree type, and we wrote like a map tree function that says, hey, if you give me a function from A to B and a tree full of A's, then we can apply the function to everything in the tree and turn it into a tree full of B's. And I think on a homework you wrote like a map rows function that takes rows tree and maps the function over that. And so these are all obviously very similar, and every time that we see something like this that's similar in Haskell, we should ask whether we can abstract out the commonality. Haskell in general gives us really great facilities for abstraction, and so we should try to abstract out what's in common. So if we try to write like a map general function, right, the only part that changes is the data type that we're mapping over. So we might try replacing that, making it polymorphic. If we say, okay, I'm given a function from A to B, and then I'm given, we'll just call it like an FA, and we'll get an FB. So F could be list, or it could be tree, it could be rows. But once again, we're going to be stuck here because let's call our function G. What do I do now? Because the way how do these work? Like the map function works by it pattern matches on the list, and then if it's empty or if it's a cons, it'll do something different in those cases, right? And these work similarly. They're going to pattern match on a tree or pattern match on a rows. But in this case, if we're writing a completely polymorphic function, we don't know what f is. There's no way we could pattern match on it. And what that even means is going to depend on what f is. Okay? So once again, we find ourselves in this situation of wanting to write something that is generic, that is polymorphic, but it actually requires knowing something, doing something different for each possible type that we could have. And so that's exactly what we use type classes for. So let's just say not possible, have to pattern match on f. Okay, so the solution is to make a type class. The interesting thing here, right, is that we're going to abstract over, the type class is going to be for things like this f, things like lists or trees or rows. And this is why I made the previous video about kinds, because f has to be a thing of kind star arrow star, right? It's something that expects one type as an input, and it gives us a type as an output. Okay, so I can say we'll make our own type class for this. Of course, it's in the standard library, but we'll call it mappy. Okay, and so this is for mappy f, and I can actually put the kind here explicitly if we enable an extension. So it's probably going to yell at me, but if okay, yeah, so it wants us to put this language extension called kind signatures, which lets us write this, but great. We don't need to put this. We could leave out the kind signature and it would infer the correct kind for it because of the way we use it. But it's nice to put it. And we want mappy, we can't call it map because that's already taken, so we'll call it, we'll just call it mappy. So mappy is going to have type, right? It's going to have this type, the general type we were trying to write before. But now we're going to get a different version of mappy for every possible f. And that's what we wanted before. Okay, so we can make a couple examples of this. So for example, if I say, instance mappy, let's do it for lists. So the thing I have to write here, I have to write the f, which in this case is like the list type constructor. Right, we saw before that we can actually write, list of A, we could write it as this thing applied to A. And so this is the part we want to put here. Okay, well, mappy now is just going to be, this is just the standard map function, so we could just say map. Right, and if we had a data type of, trees, let's say tree A, where, empty tree A and we'll call it node has an A and a tree A and a tree A. Gives us a tree A. And then we could, why is it yelling at me? I probably need GADTs, yes. Okay, so we'll enable that. But I could say now instance mappy for tree, where, well, now we can implement this directly. So mappy G, we're going to pattern match on the tree and say if it's empty, we get empty. And if it is a node containing X and a left and a right, then we'll return a node. We're going to apply the function G to X and say mappy GL, mappy GR. Okay, and that works too. So now we have this one function mappy that works either for lists or trees. We could try it out. So for example, if I say, mappy +1 on the list 1, 2, 3, I got 2, 3, 4. And if I say mappy +1 on the tree node 2, node 3 empty, empty, node 5 empty, empty. Oh right, I forgot to let's say deriving show here because it doesn't know. It's just telling me the type because it doesn't have an instance of show, so it just is saying, well, here's what type it is, but I can't actually evaluate it. Let's try that again. There we go. So every value there went up by 1, so we applied that function to everything. So this mappy class in the standard library, so mappy is called Functor. So this is actually a name that comes from the branch of math called category theory, which you don't need to understand in order to use this class, but this is an instance of a much more general kind of pattern. And the mappy function in the standard library is called fmap. I suppose the F is for functor. Really, I think it should have been called just map. And the list map should be called list map or something, but oh well. Also, it turns out that GHC can automatically write this code for us. So we can actually do this. Well, so let me just show you before I put that. So we have our mappy that we made ourselves. But if I try to do fmap +1 on that tree, so if I go back here, right, it says, no, I don't, tree is not an instance of functor. But we can actually tell GHC to write the code for us. Because this code here, I mean, there's nothing really difficult about this code. It's completely mechanical. You just pattern match on the thing, and then every time you see a value of type A, you apply the function to it, and when you see recursive things, you just like recurse on them. And if you see anything else, you just leave it alone. And it's, in fact, completely, it's not that hard to write a program to automatically generate that code for you. And so we have to enable an extension. Oops. The derive functor extension here. But once we enable that, GHC will happily generate an instance of functor for us for this tree. And so now, when I reload it, I should be able to now call fmap +1 on this tree, and I get the same thing. It does the same thing as our mappy function that we wrote ourselves. So there you go. That's the functor class, and I think either in another video or maybe in class on Friday, we will go over some other examples of using the functor class.